Now we'll study a very important concept in thermal effects of current, that is maximum power transfer theorem. Just to understand this concept, I have drawn here a figure in which a real battery is drawn, which can be drawn as a series combination of an ideal battery with an internal resistance, and it is connected across a variable resistance R. It can be treated as a rheostat also. Now in this situation, if we calculate the current in circuit, then here circuit current can be written as I is equals to E by small r plus capital R, because here we can treat both of these resistances in series. Now if we calculate the power transferred by the battery to the external resistance, this power transferred to external resistance, this can be written as this P is equals to I square R, which is the rate of heat dissipation in the external resistance, which can be written as, if we substitute the value of I, it is E square R by small r plus R whole square. The same can also be calculated by the way we already studied, that is power supplied by the battery is the power produced by battery minus the rate of heat dissipation within the battery, that is I square small r. In previous sections we already studied about it. So for any external circuit, a battery supplies the power which is given by the power produced minus the thermal power dissipated within the battery. This is another way by which we can calculate this power. But here, as there is a single resistance, we can directly calculate it by using I square R. Now here we can see the value of this power consumed by the resistance depends on the value of R. As R is variable, on changing the value of R, P also changes. And if experimentally we plot the curve which is showing the variation of this power with resistance, approximately the curve looks like this. And here we can see at a specific value of R, the value of power consumed by the resistance is maximum. And if we wish to calculate this specific value of R, what we can do is we can just find it out using the concept of maxima minima. And here we can say the value of P is maximum when dP over dR is equals to 0. So if we differentiate this expression, we can differentiate it by using quotient rule. Here in denominator it will be R plus R whole to power 4, and in numerator will keep R plus R whole square multiplied by differentiation of R will be 1. Here E square is a constant, we can ignore it, minus, if we keep this R as it is and we differentiate R plus R whole square, then on differentiating this we'll get it twice of R plus capital R, and we equate it to 0 in this situation. This square gets cancelled out, denominator can be cross multiplied with 0, and on simplifying you can see we are getting the value of R is equals to small r, because it is small r plus capital R minus 2R is 0. That means when the external resistance is equal to the internal resistance of the battery, then the power supplied by the battery to the external resistance is maximum. So this specific value of R can be written as small r, the internal resistance of the battery. And this is called maximum power transfer theorem, and this can also be written over here. We can write down the statement of the maximum power theorem, which says that power supplied by a source to an external resistance is maximum when value of external resistance is equal to the internal resistance of source. This statement is called maximum power transfer theorem. Just always keep the statement in your mind, and in coming sections we'll take up some applications by using solved examples for the same theorem.